Greetings again. I hope you've enjoyed our lectures so far on the differential calculus. Last time we looked at some optimization problems, and today will be another lecture devoted to these very important applications of calculus. I'm not exaggerating when I say that these applied problems, optimization, finding maximum values and minimum values of functions, are the heart of applied calculus. This is why calculus is so useful in disciplines such as engineering, physics, chemistry, biology, economics, etc. My classes, when I teach calculus, are full of majors from these disciplines. They're taking calculus because they need it to be successful in their majors. Their majors use these calculus skills that we're developing to solve applied problems in their discipline. Let me make another comment that I've made before on the models you'll see today. We're going to do probably three examples, three models of real-life situations. And again, they'll be fairly simple. They will not be real life in the sense that this is what an engineer would perhaps do in the job. But they will involve the skills that these engineers need, the same skills, using calculus to find maximum and minimum values. And in fact, when I develop these models, I often choose numbers so that the calculations come out as simple as possible. In real life, the numbers are never as pleasant as what we've been seeing last lecture and in this lecture. So let's get going and look at our first example. This comes from the field of journalism or printing, and it's kind of a fun problem, I think. Imagine you want to design a rectangular piece of paper that'll have a certain amount of printed material in the middle and then some margins, some white space on the outside. Let's be more specific. Let's suppose that the printed part in the middle is going to require or will want 24 square inches of print. That's the part that'll have the writing on it. And then we want a margin of 1.5 inches on the top, 1.5 inches on the bottom, and the side margins will be 1 inch each. We want to find the optimal size of this piece of paper so that it contains 24 square inches of printed material in the middle and uses the least amount of paper. We don't want to use a whole lot of paper. We want to save money. So we now want to label our figure so that we can determine the answer. And there are a couple of ways of labeling this figure. You might choose to label one side X and one side Y. I'm going to do it slightly differently. I'm going to label the printed part X by Y. So X is the vertical length of the printed part of the paper, and Y is the horizontal length. So I know that X times Y is 24, don't I? That's my fixed condition. And then I have these margins. So it's 1.5 inches above, 1.5 inches below, and 1 inch on either side. So what do I want to minimize? Well, I want to minimize the entire area of the entire piece of paper. How big is that piece of paper? Well, it's X plus its two margins, so it's X plus 3. And what's the width of my piece of paper? It's Y plus its two margins, so it's Y plus 2. So let's write this down now. The area to be minimized is the entire height, X plus 3, that's X plus the two margins, which are 1.5 each, times Y plus 2, which is the entire horizontal length of our piece of paper. And the printed part inside is fixed. It's supposed to be 24 square inches. So X times Y is 24. And now we've read the problem and we've come up with some equations. So that's often the hardest part, sort of making sense of the problem. And you might have come up with different equations. You could have modeled this, or you could have labeled your figure differently and come up with comparable equations and gotten the right answer just the same. Well, let's see. My area function, which I want to minimize, has two variables, as we've seen many times. We have to get rid of one of those variables. Thank goodness we have that condition that xy is 24, so we can solve for y. Y would be 24 over x, and plug that back into our area equation. So now we have a new version of the area equation. It's x plus 3 times y, well, y is 24 over x plus 2. And I'm going to multiply that quadratic out. Why do I choose to do that? Well, if I want to take its derivative, I don't want to use the product rule if I can help it. Why don't I multiply it out so it becomes a polynomial? And when I multiply it out, look what happens. You get a constant term which is composed of the x times 24 over x, that's 24, plus 3 times 2, that's 30. And then you get a term involving x, 2x, and a term involving the 1 over x, in other words, 72 divided by x. So there's our new area function spread out in front of us. That's the function I'm going to want to differentiate. Well, let's think about the domain a moment. What's the domain of this situation? Well, look back at the picture. X had better be bigger than 0. Duh. You don't want to have a piece of paper with no writing at all. But is there an upper bound on x? No, I don't think so. I mean, you could imagine a piece of paper and that x thing is really, really long. It could be 50. And of course, the y would be really skinny, of course. I mean, it would be very small. It would be a long, skinny piece of paper. Not a very pleasant piece of paper to read. If your newspaper comes in that form, you aren't going to buy it. So hopefully, our answer will be a normal shaped piece of paper. But mathematically speaking, there's no restriction on x except that it's greater than 0. So that's kind of curious, isn't it? It's not a closed interval like it was in some previous problems we've looked at. So now we bring in the calculus machinery. We look at our area function and say, I want to find the critical numbers. So I take its derivative, which becomes 2 minus 72 over x squared. Remember how I got that? 72 over x is really 72 times x to the minus 1. And then I use the power rule to get the 72 over x squared. And I set my derivative equal to 0 and solve for x. I'm now, in a sense, finished with the single calculus calculation, and I'm doing some more algebra. That would require that 2x squared is 72, x squared is 36, so x is equal to 6. Notice how nice this number came out to be. That's because I fixed the problem ahead of time to get a nice answer. In real life, your answers wouldn't be so nice, but that's real life for you. Is that a max or a min? Remember how we can get fooled here? Well, the second derivative is very easy to calculate here. We have the first derivative in front of us. It's 2 minus 72 over x squared. If you do the second derivative, you obtain 144 divided by x cubed. And for positive values of x, and remember that's the domain, x is greater than 0, that second derivative is always positive. What does that mean geometrically? The curve for the area is concave up. So x equals 6, being a critical number, must be at the bottom. And so it indeed is a minimum. So we have our answer. We have that x is 6, and y then would be 4 because their product is 24. And so how big is the original page, the larger page? Well, remember, x was 6, and then we had the margins, 1.5 at the top and the bottom. So that would be 9, 6 plus 3. And how about in the horizontal direction? It would be 4 plus our 2 margins, and they were 1 inch on a side. So it would be 9 by 6. Thank goodness, that's a normal sized piece of paper. You would have a piece of paper that's 9 by 6, and inside you have 24 square inches of printed material, and you have minimized the amount of paper required to create this document, to create this piece of paper. You've saved some money as a business person because you've minimized the amount of paper needed. Cool, kind of a nice problem, I thought, kind of neat. Let's kind of extract from this problem some of the skills that come into play when you're doing applied problems. I'm the first to admit that this is often thought of as being the most difficult part of calculus. My students moan and groan when we come to these word problems that require setting up a problem and drawing a picture, etc. Oh, Professor Edward, that's so hard, blah, blah, blah. What makes it difficult? Well, you're having to read something, use some geometric formulas, bring in some pre-calculus, solve some equations, etc. The calculus portion is often fairly simple, but the setup can be more difficult. What are the skills we use here? Well, we draw a picture and identify the quantities. I drew a picture and identified the x and the y as being the printed part of my piece of paper. You write some equations. What do you want to maximize and what restrictions do you have? And then hopefully you'll be able to eliminate variables so that you end up with a function of a single variable. And that's the function you want to maximize or minimize. That was the area function in the previous example. Then you bring in the calculus guns and you take its derivative, find the critical numbers, check the endpoints if there are any endpoints. In the last problem, there weren't any. But you can then use, say, the second derivative test to verify that the answer you obtained indeed is correct. In the previous example, indeed it was a minimum and not a maximum. Good. So let's do another problem. Let's try another pig pen problem. This is similar to the pig pens we saw in a few lectures ago, but I made it slightly more interesting. Now we're going to have two pig pens. They'll be side by side. And let's say the following, that we have 400 feet of fence to build our pig pens. And we want to, of course, make them as big as possible, as large as possible in area. Here's a picture of our two pig pens. They're the same size. And I'm going to label the dimensions, say x is the width of one of the pig pens and y is its length or backwards. And so we have the two pig pens like this, and there's a fence in between them. So that y is marked 3 times because of the dividing fence. You can imagine that you're a farmer and you have these pigs and you want to keep the girls and the boys separate. So you have to have a wall in between to put the boys on one side and the girls on the other side. Okay, so we want to find the dimensions of this pig pen so that the enclosed area, the sum of those two rectangles, is a maximum. And I think you can imagine that we could have been much more creative in this problem. You could have 3 pig pens, 5 pig pens. You could put imagine you're building pens and one of the sides is along a river. So you wouldn't need a fence along that side unless you have pigs that can swim, I suppose. Or you could reverse the problem and you could say, I want the area to be so much. Can I minimize the amount of fence? So here we're maximizing the area with a fixed amount of fence. You could flip it and have a fixed area and minimize the amount of fence. So let's get going on the problem. Let's solve it. What's the area of the sum of our two adjacent pig pens? Well, it's 2x times y. Good. How much fence do I have? Well, I have 400 feet of fence. And in the picture, how do I lay out that fence? Well, I'm going to have 3 pieces that are y in length. Those are the vertical pieces. And I'm going to have 4 pieces that are x in length. So I have 4x plus 3y pieces of fence, and that should equal 400. So this kind of looks familiar now, doesn't it? We have an area function with, unfortunately, 2 variables, but we have a side restriction which will permit us to eliminate one of those variables. I choose to eliminate y. You don't have to. You could eliminate the x variable if you want. And if you do that, you get that, well, you move the 4x to the other side and divide by 3. So y is 400 minus 4x, all divided by 3. And now our area function takes on a new form. It's 2x times y, but I replace y with 400 minus 4x over 3, and I multiply that out to make it a little bit easier to differentiate. It becomes 2/3 times the quantity 400x minus 4x squared. Now, before I differentiate and use the calculus, think about the domain. What's the domain of this area function? Well, clearly, x better not be 0. Or if x is 0, if you look back at your picture, you don't have a very interesting pig pen. You aren't going to fit many pigs into that pig pen. So x is clearly greater than or equal to 0, in fact, greater than 0. What about the other side? What if x is 100? Well, look back at that equation for y in a moment, right above. If x is 100, then 400 minus 4x would be 0. So if x is 100, you've used all the fence for the horizontal parts, and y is 0. Again, you aren't going to enclose many pigs in that situation. So our domain is x in between 0 and 100. All right, we have our area function. We know its domain. Let's differentiate. We get 2/3, 400 minus 8x, and we set our derivative equal to 0 to find the critical numbers. And this one's pretty nice. When you set it equal to 0, you notice that x turns out to be 50, because 400 minus 8 times 50 is 0. 50 is the critical number. Is it a max or a min, or nothing? Well, take the second derivative in this case. That's an easy way of checking. The second derivative is minus 16 over 3, and that's less than 0. Remember what that means. Your second derivative is measuring, in a sense, the concavity. It says that this curve is concave down on its entire domain, and so that 50 number must be at the top. It's a maximum. You could have also done the first derivative test. In other words, analyze the first derivative on either side of 50. You'll notice that it's increasing up to 50, decreasing afterwards, so that is a maximum there at the top. Or you could do a third technique, which is evaluate the area function at the endpoints, and of course you get 0 there, and then evaluate it at 50. Now, if I do evaluate it at 50, I plug in 50 into the area function. It turns out that the maximum area is 6,666 2/3 square feet. Just trust me, just plug in 50 into the area function. And also the y value turns out to be 200 over 3. You obtain that by plugging 50 into the y equation, and you get 200 over 3. So now I know my dimensions. It's 50 for each of the x pieces, and the height is 200 over 3. That is the optimal shape of the pig pens. It is using the fixed amount of fencing, and it's the maximum amount of area. Let me look at this visually just for a moment. You can graph this area function on its domain 0 to 100, and you see that indeed it is concave down, and that point 50 is the maximum value there at the top. Good. Let's do one more example, and this one I really like. This one's kind of neat. I think you'll see that it's quite realistic in the idea. Of course, we're going to simplify so we can actually solve it, but it's a problem that I'm sure oil companies, oil refineries face a lot. I know off Santa Barbara there are oil wells in the water there, and imagine you have the following situation with offshore oil rigs. So the well, we'll be specific, is 2 kilometers offshore. And then you have a refinery down the coast, and we'll call it 4 kilometers down the coast. Let me show you a picture of what I mean. So the oil well is 2 kilometers off the shore. It's in the water. And it's 2 kilometers as a perpendicular distance to the coast. And then 4 kilometers down the coast is the refinery. And you want to ship the oil from your oil well to the refinery. Okay? Well, how are you going to do it? Well, suppose for this problem that it's twice as expensive to put pipes in the ocean as it is on land. Now, I'm not sure how realistic that is, but you can imagine a more complicated model, but the idea is the same. Let's say it's twice as expensive to put the pipe in the ocean as it is on land. For instance, it might cost $1 million a kilometer on the land, and so on the ocean it's $2 million a kilometer, twice as much. So there's going to be a proportionality constant in this model. In other words, there'll be a number k, which you can think of as being 1 million. So if it costs $1 million a kilometer on land, it costs $2 million a kilometer in the ocean. And of course, what do we want to do with this problem? We want to minimize the cost. You're constructing this oil refinery and this oil well. You want to spend the least amount of money. So what path should you use to get the oil to the refinery? Here's a picture, again, of our situation, and I've drawn a typical path. In other words, you lay a pipe that goes to the land in between the perpendicular intersection point and the refinery. So in this picture, for a while the oil travels in the water, and then it goes horizontally down to the refinery on land. And I chose to label X the distance between the perpendicular intersection point and where the pipe hits the land. And remember, 2 is the vertical distance from the well to the land. And if I label X that leg of the triangle, then 4 minus X is the rest of the distance. So in this picture, the cost would be what? Well, the cost of laying the pipe would be 2k, remember k is that proportionality constant, times the square root of x squared plus 4. Where did that come from? Well, the hypotenuse of this triangle by the Pythagorean theorem is 4 plus x squared, all square rooted. And that's the length of the pipe that's in the water. So it costs twice as much in the water, so that's why that 2 is there. So it's like 2 million times that length. Now what about the rest of the pipe? Now it's on land a distance of 4 minus x. So on land the cost is k, not 2k, but now, because remember it's cheaper on land, k times its distance, 4 minus x. Wow, that's kind of complicated, but that's our cost function. One good thing about this, there's only one variable in it, variable x. K is a constant. In fact, we'll discover in a few minutes that the k flushes away. It won't be important in the final answer. We're trying to find the x value. We're trying to find the point where the pipe hits land. That's what we're trying to find. We're trying to find x. Well, x is clearly between 0 and 4. It would be kind of dumb to have x go, say, to 5 and then go backwards to the refinery. So I think it's pretty clear that x should be between 0 and 4. That's the domain of our cost function. And here's something I suggest in a lot of these problems. Before you actually use calculus, plug in some typical values to get a feel for what's going on here, to sort of get an idea of some of the costs that are involved. For instance, suppose I plug in 4 for x. What does that mean geometrically? If x is equal to 4, that means that the entire pipe is in the water, doesn't it? It means I don't even go on land at all. We just say, go directly from the well to the refinery, all in the water. Well, if you plug 4 into your cost equation, let me show you how I do that. I plug 4 in for x, and I get 2k times 4 squared plus 4, all square rooted. That turns out to be 16 plus 4, or 20, so square root of 20. And then the next term is 0, because x is 4. And that, with a calculator, click, 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 you get 8.9k approximately. Now, how about if x is 0? What does that mean geometrically? If x is 0, you would say, go directly to the shore, go 2 kilometers, right to shore, and then motor your pipe all the way down to the refinery. That's what would happen if x were 0. What's our cost function now if x is 0? Well, you would plug in 0 for x, and you would get 2k times the square root of 4, or 2, plus, and if x is 0 in the second term, you get 4k, so you get 8k. Slightly cheaper, isn't it? I've saved some money with that path. How about if I say pick a midpoint? What if I pick x to be 2? So that's picking the midpoint between 0 and 4. And if you plug that in, you get 2k times the square root of 8 plus 2k. And that is, again, using my calculator, approximately 7.657, which is even better. So it looks like the endpoints aren't going to be one of my answers. It looks like we can do better because we've already got a better answer here. But is that optimal? And by the way, you'd want the optimal solution if you were working for an oil company, because K might be $1 billion, not $1 million. And so if you can do better, you're saving lots of money. So now let's do the calculus. Our function is, of course, 2k times the square root of x squared plus 4 plus k times 4 minus x. I take its derivative. That requires the chain rule. And I get 2k times 1/2 x squared plus 4 to the minus 1/2 times the inside derivative 2x. And then the derivative of the second term is just minus k. That's pretty simple. And I simplify it slightly. Some of the 2's cancel. And you get that the first derivative is 2xk over square root x squared plus 4 minus k. Good. I want the critical numbers. Set the first derivative equal to 0, which means I have to have 2xk over square root x squared plus 4 equal to k. And as I said earlier, the k's flush away. They're gone. You cancel the k on both sides. And you get that 2x equals the square root of x squared plus 4. I obtain that by first canceling the k's and then multiplying both sides by square root of x squared plus 4, and now some simple algebra. Square both sides, and you get 4x squared equals x squared plus 4. Subtract off x squared, you get 3x squared equals 4, and x turns out to be 2 over the square root of 3, which is about 1.15. A little bit less than x equals 2 that we looked at earlier. And I claim this is a minimum because it's smaller than the endpoints. And remember, the absolute minimum can occur either at the endpoints or at a critical number. That's one of the basic principles of calculus. Here is the only critical number, and if you plug it into the cost function, you get 7.4641k approximately. And that is clearly less than the 2 endpoints. Notice also that it's less than using x equals 2. So we save some money by going to 2 over square root of 3 for our value of x. Great. Okay. Believe it or not, I'm sort of happy to say we are, for the moment, finished with what we like to call in calculus courses the differential calculus. Wow, congratulations for hanging with me. We've looked at the tangent line problem, and then we did some limits. We did the derivative, and we saw a whole lot of formulas for calculating derivatives. And then we analyzed graphs, increasing, decreasing, concavity. We did some max-min problems, optimization problems. We also looked at velocity. And in this lecture and the last lecture, we looked at some kind of complicated applications of the differential calculus. In our next few lectures, we will start what we like to call the integral calculus. We'll look at something called integrals. And this will have many, many more applications in calculating volumes and the length of curves and how much work it takes to push something along the ground. It has many, many applications as well. And then we'll have a real surprising result that these two topics, the differential calculus and the integral calculus, are intimately linked together. So, thanks very much, and I look forward to seeing you next time.